Welcome! In this video, I'll give an intro to rocket composition and concepts, as well as a preview of our lab. We'll be using apprentice rockets, which come unmodified with 3-fin fin cans and ogive nose cones. Participants in this lab will get to experience these concepts through virtual modeling in Fusion 360 and Open Rocket programs, allowing participants to both model their own objects and run flight trajectory simulations. Let's start with an overview of the components of a model rocket. The body tube is the bulk of the rocket. While not serving any dynamic purpose, it exists as the structure of the rocket. All the pieces are connected to it or lay inside of it. The fin can is connected to the aft of the rocket and provides stability. Inside the fin can and body tube is the motor retainer, with 2 centering rings at the fore and aft of the tube and a motor stop at the end. A motor can be easily slipped into the tube for launch. Before launch, this metal hook ensures the motor does not fall out of the rocket. Once lit, however, the motor will be propelled upward and falling out downward is no longer a worry. The motor to be used in this model is the Estes A83 motor. Once the motor has burned its propellant, it'll burn a 3-second delay fuse before exploding a charge within the rocket to release the parachute. While the fin can and body tube are rigidly connected by superglue or other adhesive, the nose cone is only held inside the tube by friction. A parachute is attached to the nose cone and then attached to the body tube with a shock cord. This parachute is stuffed inside the body tube and held in by the nose cone. Once the charge goes off, the explosion forces the nose cone off and the parachute is allowed to deploy for a safe recovery. Now let's go over some rocket concepts. In model rocketry, 3 major factors which affect the expected trajectory of the flight are the thrust force of the rocket's motor, the drag force acting upon the rocket body, and the stability of the rocket overall. Thrust is the force that propels the rocket through the air. With our motor, it is generated by expelling mass at high speeds out the back of the rocket, therefore propelling the rocket forward. Drag is a mechanical force that opposes a rocket's flight. It's generated by the contact of the air on the body of the rocket throughout its flight. The more surface area a rocket has, the more drag it will experience. Stability is the final important factor when one wants it to achieve the highest possible altitude of a model rocket. An unstable rocket will likely have an unpredictable flight path, increasing the likelihood that the rocket won't travel directly upwards in its flight. In the first part of our lab, participants will be able to create a 3D model of the component they're modifying. This will be done using Autodesk Fusion, a program that facilitates computer-aided design. For a brief preview of this process, see how an unmodified fin can looks assembled in the program. This model has the standard number of fins, 3. However, in our lab, participants can increase or even decrease this number as they'd like. Participants will also be able to modify the nose cone in Autodesk Fusion however they'd like. After creating 3D models of the modified parts, participants will be able to simulate the flight of a rocket with these pieces using Open Rocket, a program specifically designed for these types of simulations. Here is a diagram of an unmodified apprentice rocket modeled in the program. From here, participants can edit the nose cone and fin can components to match their modified versions. From the flight simulations, we can see the rocket's predicted apogee, maximum velocity, and maximum acceleration along with other information on its flight. In the diagram, the rocket's center of gravity and center of pressure are also labeled. We can toggle between viewing the blueprint and a 3D model using the View Type tab. For an even better look at the rocket's predicted flight, Open Rocket can create a graph of the rocket's vertical motion versus time. This means its altitude, vertical velocity, and vertical acceleration. Marked on the graph will also be the motor's ignition and burnout points, as well as the rocket's apogee and recovery device deployment. The launch of a model rocket has 3 phases. The thrust phase, in which the motor is actively propelling the rocket upwards. The coast phase, in which the momentum that the rocket has after the thrust phase continues to force the rocket to coast upwards. and then the recovery phase, in which the rocket falls back down after reaching apogee, or the highest point of altitude. Once the motor is burnt out, how much higher the rocket reaches is dependent on its velocity at burnout, how much downward force it experiences from drag, and its stability.